Okay, so the end of question number 11, or where we were, was 6.655 times 10 to the 6th meters. That's the radius of orbit. But the question wants to know how high above the center of the Earth. So just going up here to this empty space, right? So here's the Earth. And so what we just found was this whole thing, the radius of orbit. But the question wants to know, what's this height? And so to find it, we need to subtract the radius of the Earth. So you can look up in the back of your textbook on page 955 that the radius of the Earth is 6.38 times 10 to the 6 meters. So if we go back down here to this question, so radius of the Earth, little r, because it's the radius of the Earth, will be equal to the radius of the orbit. Whoops, no, that's not what I want. I want height of the satellite will be equal to the radius of the orbit minus the radius of the Earth. So we're going to subtract from this the 6.38 times 10 to the 6 meters. And when you do, you should get a height of 2.75 times 10 to the 5th meters. So this is how high it is above the surface of the Earth. Okay, which is what number 11 is asking. All right, number 12. How fast is the moon moving in its orbit as it orbits Earth at a distance of 3.84 times 10 to the 5th kilometers? So it's telling us the radius, 3.84 times 10 to the 5th kilometers will be 10 to the 8th meters. And it wants to know how fast, and it's orbiting the Earth. So we know the mass of the central body is 5.98 times 10 to the 24th, because that's the mass of the Earth in your chart again in the back of the book. And if we're looking for V, then the easiest one to use is this guy. V squared is equal to G, mass of the central body, over R. Okay? So V squared is equal to G, mass of the Earth, over R. So 6.673, gonna run out of room, times 10 to the negative 11, it's only 11 there, Newton meters squared per kilogram squared. And that's going to be times 5.98 to the 24th kilograms. And it's going to get divided then by this 3.84 times 10 to the 8th meters. And remember, that's going to be V squared. So you're going to need to take the square root. And when you do, what you get before you take the square root is 1.39 or something like that, times 10 to the 6th. And then meters squared per second squared. And when you take the square root, you get 1019.40 meters per second. Now your other option is you could have done V is equal to 2 pi r over t. And you could have looked the t up in the back of your book for the period of the moon. But I would say go this way because you probably already know the mass of the Earth. If you do it this way, period of the moon is 2.36 to the 6th. And you end up getting 1,022.35 meters per second. It's a little bit different, and that's because the mass of the Earth would be rounded, the period would be rounded. It's just rounding in different spots. So not to worry, whichever way you choose, I'll be able to handle it because I'll have answers for both of them. Okay, so this was number 12. Number 13. On one of the Apollo lunar missions, the command module was placed in a very low, approximately circular orbit above the moon. Soon the average height, so they're telling us the height, is 60 kilometers, or 60,000 meters above the surface, and the moon's radius, that's the radius of the moon, not of the orbit, is 7,738 kilometers. And so we need the radius of the module. And so it's going to be the radius of the moon plus the height, right? So here's the moon, here's the object, this is the 60 kilometers, and this is the 7,738. So you need to add them together. Before putting the zeros in, I'm going to add them together. So 7,738 kilometers plus 60 kilometers. So the radius will be 7,798 kilometers, or 7,798,000 meters. Okay, so we now have the radius of orbit, and it wants to know what's the period of the orbit. Okay, so I would probably do Newton's version of Kepler's third law and do g mass of the moon this time, because that's the central body, over 4 pi squared is equal to r cubed over t squared. And it's looking for the period. So rearrange this for t. So take the t squared up, take the 4 pi squared up, and bring the g mass of the moon down. So t squared will equal 4 pi squared. We just found the radius, 7,798,000 meters, and that's going to be cubed over 6.673 to the negative 11 Newton meters squared per kilogram squared. And then in the back of the book, if you look up the mass of the moon, it's 7.36 times 10, and I think that's 22 if I could see it, 22 kilograms. Okay, so try to remember to cube your r, square your pi, punch it in, and you're going to get a t squared of 3.812, I think it's 2, to the 9th, second squared. Take the square root, 6.174, I believe. I can't tell if it's 4 or 5. I think it's 4. I can't make up my own writing. Times 10 to the 4th, just because it's too tiny, seconds. And then there's a part B that wants to know how fast is it going. Well, now that you have the period, you might want to do v is equal to 2 pi r over t, because you have the period in your calculator. So 2 pi brackets 7,798,000 meters divided by 6.17, whatever that number is in your calculator, even though I can't see that digit. And you should get 793.611 meters per second. I can make out the ones. I just can't tell the 5s from the 4s. Okay, so that's number 14. Number 15. No, that was number 13. Number 14 says, a star at the edge of the Andromeda galaxy appears to be orbiting the center of that galaxy at a speed, so they're telling us v is equal to 2 times 10 to the 2 kilometers per second. Now this is not kilometers per hour, so you are not going to change it by doing a 3.6 factor here. It's just kilometers you need to change, multiply by 1,000. So 2 times 10 to the 5th meters per second is our speed. The star is about 5 times 10 to the 9th astronomical units from the center of the galaxy. Calculate the rough estimate of the mass of the Andromeda galaxy. Okay, so we're looking for the mass of the central body. Now, that 5 times 10 to the 9th AUs, and it tells you in brackets, 1 AU is 1.49 times 10 to the 8th kilometers, or 10 to the 11th meters. This is the distance between the Earth and the Sun. Okay, and so it's just, instead of using a huge number, we use this as a multiplication factor. I'm going to run out of time and I'll have to come back.